So in class, we were talking about the fact that magnets come in two types, north and south, and they tend to come together in a dipole. A dipole magnet has a north and a south pole. The typical bar magnet that you used in elementary school looks like the drawing here. It's not always clear with permanent magnets where their poles are, like the little button magnets I was playing with in class. I'm not even sure where the north and south pole is, but it was probably some kind of dipole magnet. There are other kinds of magnets, quadrupole magnets. They have more than two poles. But in any case, your typical magnet has the two poles, north and south. It's like having a plus charge and a minus charge together. We had the electric dipole. So it was mentioned in class the other day that that north and south poles are difficult to separate, that magnets actually come in dipoles, as opposed to electric dipoles where we can separate the charges and we can find plus charges and minus charges separate from each other. We'll talk about that in a little bit. As we said, a current carrying wire also has a magnetic field, so we call that an electromagnet if we use it as a magnet. Note that all current carrying wires have magnetic fields, so any circuit that we build, when we put a current through it, they have magnetic fields. They're different from the magnetic field of a current carrying wire is different from a permanent magnet, because you can turn it on or off by turning the current on or off, and change the size by changing the current. So electromagnets are actually pretty useful things. We just didn't think of current carrying wires as electromagnets previously because we didn't need to use them as magnets. The field of a single current carrying wire isn't that big anyway. We can sort of ignore it until it becomes big enough that it matters. The magnetic field near the wires in any given circuit is definitely measurable, but it falls off, as we said in class the other day, 1 over r squared. So we really just talk about sometimes if we care about the magnetic field near wires. When we get farther away, it doesn't matter. You're not going to be impacted by the wires in the walls unless you're right next to them, and in any case, still not bad for you. If we want to intensify that field, we make a coil. We can make a magnetic field more intense by coiling up the wire, and that gives us a larger magnetic field. We call that a solenoid. And the way that makes it more intense is because each loop of wire has a magnetic field, and then we're adding up a bunch of loops to get a bigger magnetic field inside the coil. Again, we'll address this more later. So a single loop of wire, if you take one of those loops of the coil and you run a current through it, a single loop of wire actually acts like a magnetic dipole. So if we want to create a magnetic dipole out of an electromagnet, we create a single loop. So I've drawn in here what the single loop of wire looks like in terms of a magnet. If we treat it like a magnet, it looks like a little dipole magnet. Note that when we say a single loop of wire with a current, that is the same as a charge, right? A current is a moving charge. So if you have a charge that's moving in a circle, that's the same as a current moving in a loop, right? Because a current moving in a loop is charges moving in a circle. So a single charge, or any number of charges moving, also have a magnetic field, right? Moving charges have magnetic fields. This is what it means when we say currents have magnetic fields. So moving charges have magnetic fields. So the fundamental unit, in a sense, of electromagnetic field is a single electron moving in a loop. A single electron moving in a loop acts like a little dipole magnet, a little tiny dipole magnet, and we actually, and the electron moving in a circle, we give it a name. It's called the electric dipole moment of the electron. Classically, electrons and atoms move in circles, and so those classically they have electric dipole moments. So we'll address a lot of these things again later, but just recognize that moving charges create magnetic fields, therefore currents create magnetic fields, and we can make loops that are dipole magnets, and then coils which make bigger magnetic fields, and your typical electromagnet is just a coil or a solenoid of wire. Now getting back to permanent magnets, the permanent magnets are the kind of magnets that we can literally dig out of the ground, right? That they hold a magnetic field. They're not to do with us putting currents in wires. And there are 3 types of permanent magnets. well, there are more than three types. There are three common types of permanent magnets. There are ferromagnets. Those are the kinds of magnets that you played with in the classroom in school when you were little. The bar magnets, the iron magnets. Ferro means iron. So the ferromagnets are magnets which are by definition are magnets that can hold a magnetic field. So iron certainly is the common one, is the one that was discovered hundreds of years ago. But any magnetic material, any permanent magnetic material that can hold a magnetic field permanently is called a ferromagnet. A paramagnet is something that can become magnetized when you bring a magnetic field near it, and it will become magnetized in the same way as the magnet. So you can make something like, for example, aluminum, which is not a ferromagnet, doesn't hold a permanent magnetic field. You can magnetize it by bringing a magnetic field in its vicinity. That magnetizes it while there's a magnetic field in its vicinity. A diamagnet, same idea. It can become magnetized when a magnetic field is in its vicinity, and then it will be unmagnetized when the magnetic field goes away. But it's just magnetized in the opposite direction. So the field is actually in the opposite direction of a paramagnet. So we've been talking about the fields of magnets. We need to define something about fields. Remember what a field is. A field means that you can have a force at distance. So if you have a magnet in the vicinity of another magnet, and they're at a distance from each other, they exert a force on each other. We say, how do they exert a force on each other? They exert a force on each other because they each create a field around them, and they can exert a force at a distance. As we said in class, north poles repel north poles, and south poles repel south poles, while north poles attract south poles, and south poles attract north poles. So we know that there is a field around magnets because we can feel a magnetic force at a distance, and we discussed how that's different than electric force. We know it's not an electric force. So there is something called a magnetic field that is around a magnet. I've just indicated here, if you had two dipole magnets near each other, you can see that there are going to be forces between them, and those two magnets will tend to line up and then attract to each other. Whoops. So we give the magnetic field a letter, like we did. Electric field was E, right? The magnetic field is B, the magnetic field. Analogous to the electric field due to electric charges, the magnetic field is due to these magnetic charges, north and south. It's a vector, and it has MKS units over the Tesla. Another common unit is the Gauss, and the reason why we bring that up is because the Tesla is actually a pretty large field, and the Gauss is more common kinds of size of fields that we run into on a daily basis. The Earth, as we mentioned in class the other day, of course, has a magnetic field, and the Earth acts like a dipole magnet. So I'm going to draw a dipole magnet on top of the Earth. And the field near the surface of the Earth is about 1 Gauss. It's less than 1 Gauss, but it's on the order of a Gauss. Whereas on the other hand, your typical refrigerator magnet, might be about 50 Gauss, and those neodymium magnets that we were playing with in class, they can range up to half a Tesla. They're actually, as we said, those fields, those magnets are actually pretty strong compared to other kinds of magnets that we've played with. Going back to the Earth, let's think about the Earth's magnetic field. It acts like a dipole magnet. It's got a magnetic field. The magnetic field has a north pole and a south pole. And think about what happens when you take a magnet near the surface of the Earth. If you're standing on the Earth and you use a compass, let's say, and a compass is actually is something that, a compass is just a magnet which lines itself up in the magnetic field, and the north end of the compass, which is the north end of the magnet that you're holding, the compass magnet that you're holding, points towards geographic north of the Earth, and the south end of the compass will line up towards the south end of the Earth. So the north end of your compass points towards the geographic North Pole, and the south end of your compass points towards the geographic South Pole. So what does that make the Earth's field? The Earth's bar magnet, right? The Earth acts like a bar magnet, but if the North Pole of your magnet points towards the geographic North Pole where Santa lives, and the South Pole of your magnet points towards the geographic South Pole where the penguins live, but think about the magnet, a South Pole must point towards the North Pole, and a North Pole must point towards the South Pole. So the geographic North Pole is the magnetic South Pole, and the geographic South Pole is the magnetic North Pole. Now, we have to be even a little bit more careful than that, and it turns out that the geographic North Pole is not exactly the same place as the magnetic South Pole, and the geographic South Pole is not exactly the same place as the magnetic North Pole. They're pretty close to each other, but they're off by a little bit. We can map the magnetic field, just like we map the electric field, and the dipole magnet, right? So dipole magnet, you've done this in elementary school. You've taken iron filings and you've put them around, you've poured them around dipole magnets, and you see that the map looks a lot like the electric field map. The field lines, still the same idea as the electric field lines. A couple things to note is that magnetic field lines point from north, away from north poles and towards south poles. So north is like the positive charge and south is like the negative charge. Magnetic field lines cannot cross each other. It doesn't make sense for them to cross each other because by definition it's the direction of the force on a north pole at that point, and there is only one possible direction, so there's no magnetic field lines crossing. And as the magnetic field lines get less dense, that means the magnetic field is smaller. So the magnetic field is going to get smaller as we get farther away. Whoops, B decreases. Magnetic field gets smaller as we get farther away from the magnet, so the field lines get less dense. So just like electric field lines, magnetic field maps are very similar.